everyone for coming. Let me introduce myself. I'm Hongchao, and I work from CoreOS. I work on Kubernetes scalability mostly. And tonight, I'm going to talk about Kubernetes and discuss some techniques we use when dealing with performance of large-scale distributed systems. Before I talk about performance, I want to talk about what's so great about Kubernetes. Because if a system wasn't so great, we wouldn't bother our time improving its performance. So Kubernetes is a cluster management tool for containers. It's inspired by Google internal experience for managing containers for 10 years. It supports multiple container runtime, Docker and Rocket. It's open source, written in Go. Kubernetes focuses on an abstraction called service. So basically, when you write in an app, your apps talk to each other not by IP addresses, but by their service names. A service usually consists of, Kubernetes does provides built-in name discovery, so it's discovery. And a service usually consists of a set of parts, backends, that Kubernetes does load balancing, auto scaling for you so that you don't need to worry about failures that cause services goes completely down. When you are building infrastructure, you want your infrastructure to be immutable. That means when you are doing upgrade, you want to keep the old things and start running new versions of services or applying new configurations. And if something goes wrong, you can roll back safely. And Kubernetes support that as well. It's called deployment rolling upgrade. So from architecture point of view, Kubernetes consists of two parts: the master components and the workers. The master assigns work, manages cluster health, and provides central knowledge. Workers is doing the work. In this case, it's running the containers. In master component, we had two main components, which is scheduler. It makes the decisions, binding the parts to the nodes, which is assigning the work. And also an API server. It provides the web services. When you do kubectl, it's talking to that web services. And it also manages the cluster states, like scheduler and controller manager talk to API server to get those states in order to do the work. So when we start working on Kubernetes scalability, we ask ourselves these questions. What are the current performance metrics of large-scale, large cluster? At that point of time, the large means 1,000 nodes and 30K parts. And we also want to know where are the bottlenecks. Specifically, we want to understand what's happening internally when doing high throughput of workload. We need some strategy of testing. First, we run experiments in simulated environment. So I saw some argue that we are not handling real use cases. I just want to say that when pushing forward scalability, we want to pushing the edges. And 3 months ago, when we were doing it, the edge was kind of the 1,000 nodes. I know very few people were running 1,000 nodes cluster at that point of time. However, if we do something that no one else can reproduce in their environment, it's going to be really bad in open source work. So as a result, we need to have an easy way to simulate out the trivial things and test only the key components and have other people can reproduce it in their environment as well. The simulation usually is more lightweight and costs less resources and time. And so we are also doing performance testing. That means we put a huge workload and let the system do the work and calculate how long the system finish the work. And in Kubernetes, there's something called density test, which measures how long it takes to run 30 parts per node. So in 1,000 nodes, it's finish 30K parts evenly on each node. And here's one example what the density test looks like. Here's 100 nodes. It finishes everything. We also have a plotting tool to visualize the results. I just want to emphasize here that when we are talking to other people, like it's sometimes people show their results with 1 megabyte log file. Like that usually doesn't work. It's better to show diagram to humans. In the following, I'll talk about like 4 techniques that we use in performance debugging. The first thing, check the hardware. So usually when we start, we checking the performance bottleneck. Like we first need to check if any hardware resources was used up. So like for example, like CPU or memory could be used up. In this case, the performance wouldn't be good. Like and if we add more resources, we can simply improve the performance. So one good example here is like recently there's a Docker over Kubernetes blog post. In the blog post, it uses kind of like machine with 4 CPUs. That's just insane. I mean, but it's really a good example here. Like it reminds us that how often people forget to check the hardware first. So in Kubernetes, they usually use like tens of gigabytes of memories and like more than 4 CPUs, master component. And we can just use the talk command, which is built-in command tool for all Linux systems. The second thing to look at is the metrics. Metrics provides a convenient view into the system. So without metrics, you're pretty much like blind to a system. And like latency metrics can help us find low-hanging fruit. We can look into the system and see which latency metric is going high, and that could possibly become a problem. And for critical and complicated components, we can simply, we should add more metrics to narrow down the problem scope. Kubernetes use like Prometheus Metrics, and here's what it looks like. And here's one example in Kubernetes environment that we find out previously. So here, if we look at like, here's the mouse. When it creates a pod, like on the client, the usual latency is 1 millisecond, but the spike latency goes up to like 50 milliseconds. And in the API server, the rest response for the client is usually 1 millisecond. And in the scheduler, it's pulling pods at 1 millisecond, and the scheduling latency is like 7 milliseconds. That's 8 milliseconds in combined. So in this diagram, we can easily see that like the client is problematic because like it goes up to 50 milliseconds, and that potentially becomes a bottleneck because it's larger than everything else. But like matches is not so great if we use matches to find bottlenecks in one component become problematic. We need to dig further what goes wrong specifically. And matches only provides coarse grain like knowledge. We don't want to read the entire code base and like imagine the runtime performance. So what we can do is like we usually do profiling. Profiling provides insights into the system where the CPU or memory is spent. And it's very trivial to do in Go. All right. So I should put, where's my mouse? Wait. Am I easier? Just go on the side. That's much easier. Right. So here's the program I wrote. Now I just copy paste from Stack Overflow, but like I add the profiling. So basically it does like calculate the prime factors, and it's gonna cost a lot of time if we look at this. Wait. Yeah. So this is a program, right? And if we run it, like I already compiled it, it's like gonna be like CPU profile and D1P profile. Because it takes a lot of time, I won't show here, but like I already generated the file, and we can simply once you run it, you can get the profile file, and I can dig into the profiling thing here. And here we saw that like we can simply figure out which is causing a lot of time. You see like total time is about 150 seconds, and this single function is taking like 40 seconds, which is time consuming. All right. Let's go back to the slides. Okay. All right. I can see it. All right, yeah. But during the profiling thing, we gain a significant improvement in the Kubernetes scheduler. And yeah, and finally, like I want to talk about like besides the benchmark thing, like we just see profiling, we can also do remote profiling. So basically, when you're running a server, it never goes down, like it never stops. And at that point, like we can get some real-time profiling when server is running. The main step is like we're going to enable a profiling in the server code, which is open a port, and you can get matches profiling from it, and we should allow the port in firewall, and finally we can do the command line. So I'm going to show another demo here. Wait. Yeah. It's so complicated. So if you look at this thing, right. Yeah, here I am gonna listen on this port, which is gonna let you do the profiling, and it's also doing a prime factor here, and I'm gonna like choose a very magic number. This thing is gonna take a long time. D2, and I'm gonna curl. Right, we're just gonna kill this file. And this thing is just going crazy. And here we can do P profile, HTTP. And did I have it? Yeah, I have it. So basically, it's gonna like get some the default window. Like you can set the window, but the default window is 30 seconds. You're gonna get the profiling, CPU profiling for 30 seconds here. Let's wait 30 seconds. So it's still running because it takes a lot of time. This factoring thing is gonna wait forever. Yeah. So if we look at this file, like it shows, like this is the runtime profiling. We can see like, yeah, it's the same thing. Like it's the same thing as previous thing. It's like this function filter. It's taking a lot of time when doing prime refactors. So even though we have no idea what the code does, we can understand the internals and see what's the bottleneck here. Wait. A way to convince and review and plotting to talk to humans. Right. What's going on? Sorry, I saw a lot of things going on here. Yeah. All right, I know what's going on here. The server is still doing prime factoring. Yeah. Like the CPU goes like crazy. All right, so there's one other thing we are recently doing. It's SCD-free, SCD-free integration with Kubernetes. SCD-free is a major step forward to beyond SCD2. I just want to shout out some benefits of using SCD-free. It keeps millions of keys in memory. And it sends a watch progress update so that you can have like you don't need to do the release if like you get the kind of like compatible error. And it uses gRPC, which is very efficient encoding and thing. And it kind of reuse the connection for different watches and clients. And it uses one lease client. So previously, when you do the TTL is kind of like per key TTL. It's byte to the key and byte to. So this list thing it's more efficient and it's not bound to the session. And it supports like media transaction. So you can, it's a single if-else layer, and you can put multiple get and outputs in a single operation. Finally, it's about like SSD3 is way more reliable. It can run with gigabytes of keys in memory without any pause during snapshot. And integration with Kubernetes is happening. It's aimed for the 1.3 releases, and it solves the major problems and brings powerful features, as we just saw. The current progress is checking the issue. Great, that's my talk today. Thanks.
Anybody have any questions for Hongchao on improvements to Kubernetes performance? No? Well, if not, thanks very much for that, Bud, and thanks all of you guys for coming. Yeah, I know, guys, but thanks for pointing. I do want to remind everybody. Oh, a question. I'm sorry. Please go ahead.
I think so.
Good answer. That's awesome. Okay. And what about the HTTP3 API?
Huh?
The HTTP3 API?
Can we talk offline? Like the Xiang is over there. Yeah. Okay. Great.
Anybody have any questions for Hongchao on improvements to Kubernetes performance? No? Well, if not, thanks very much for that, Bud, and thanks all of you guys for coming. Yeah, I know, guys, but thanks for pointing. I do want to remind everybody. Oh, a question. I'm sorry. Please go ahead.
What release are these 4 or 5 going to be version 1.2?
I think so.
Good answer. That's awesome. Okay. And what about the HTTP3 API?
Huh?
The HTTP3 API?
Can we talk offline? Like the Xiang is over there. Yeah. Okay. Great.